Awesome. Set up. I just checked I've just deployed the website and it's just finished. So it couldn't be better timing. Okay, great. Can you see my screen and hear me? Yeah, cool. Okay, so thank you so much for coming. This is very exciting. And yeah, I'm a bit overwhelmed with how many people both signed up and showed up. Um, but in some ways, right, that may be a sign that there is a demand for looking into paraanalysis and what we do when we do paraanalysis and why we do it. And as Heidi mentioned, my sort of I don't know, skills in paraanalysis were really developed in a ManyBabies project. So I was on the data analysis team for ManyBabies 5. And I really want to emphasize that this sort of data simulation approach and everything I'll be talking about today from the sort of general approach and the code comes from these sessions that we had at these data analysis meetings. And I would say that these sessions, data analysis sessions, were really guided by curiosity, first of all, but also with a sort of what if mindset. And we really went down a rabbit hole in the sense of thinking, well, what if we suddenly had heteroskedasticity, right? Well, how would that affect the power estimates that we have available for this study? What if we vary the standard deviation of intercepts? What happens then? And it's really this curiosity-driven learning that I hope you'll get from this workshop today. Because I think there's some nuance to paraanalysis that's often missed in the sense that it's often construed as this way of calculating a threshold, right? As soon as we're above that threshold, we're fine. But really, there's more nuance to it. And I want to make the case for really seeing paraanalysis as a tool for study design. So I think that's what we're going to get out of today, hopefully. Okay, so with that in mind, some practical information and an overview of what we'll be doing today. So we'll start with just a brief talk on paraanalysis and what it is and why we do it, what it's useful for. I then prepared a little R Markdown file for you to do your first data simulation, or if it is your first. But taking you through an experiment on looking time, infant looking time, which should be a sort of domain that's familiar to a lot of us here in developmental science. Then I'll talk about cumulative science. So how can we? So we'll then meet again, right? I'll put you out into breakout rooms, and then we'll return. Then I'll talk about cumulative science and how should we model effect sizes and how can we gain the most from these cumulative science efforts, such as meta-analyses and multi-lab replications. And then you'll do some power analysis in R. So another R Markdown file, building on the data simulation functions that you made in the first break. Okay. And then questions or discussions, or we can meet and discuss how we found it all and what we can use it for. Okay, and all code, materials, recordings will be made available after the workshop. So yeah, again, don't worry if you can't understand the code, it'll be there for eternity. So you can really reanalyze the what's going on in the code if you want. And then since we're so many, right, I'd also appreciate it if we could help each other a bit. So when we go out into the breakout rooms, maybe the people who are very affluent could help those who are less affluent. And I said it was a workshop for everyone. And I think it is, because you can look at the website and see the code outputs. But if you could help each other, because I don't think me or Quinn can come around to all of the different breakout rooms in time. So yeah, great. That would be great if we could do that. Okay, I feel there are so many of you here. I feel like we should be talking about we should be starting a revolution or talking about that sort of power in terms of the precarity of young researchers. We'll stick to statistical power for now. And we'll talk about these three things. So we'll talk about some theory and background on power analyses. And then again, we'll focus in on the process of data simulation. How do we actually simulate data? And then simulation-based power analysis. So how can we really explore the multiverse of decisions for parameters that we can set? Yes. Okay, so if we start with theories of, or the theory behind statistical power. And the first question we need to ask is, why is it important, I think, even before we delve into the details of statistical power? And we need to be careful of, statistical power in many fields, right, has been calculated as being around 50%. And this is true for neuroscience, psychology, developmental science. I think it's below that. I think it was 43%, something like that. And really, this is an important figure, right? And because what it means is that if there is a significant effect in the populations that we're interested in, right? If there is a significant effect size, then we only have 44% probability of detecting it. And that means about half of studies across the world, right, have false negative rates or false null effects. And it's hard to build theories. It's hard to construct explanations for why things occur, for why our studies show the results they do, when around half of them actually don't show the effects that are there, right? So this is important, and statistical power is important. And rather than, so the threshold generally, right, is set at around 80%. So we're willing to accept a type 2 error of around 20%. But really, it's more nuanced than that, right? We need to figure out, we need to make inferences about whether the data that we collect based on this study design can tell us something about the world in a sensitive way, right? Is it sensitive to detecting the effects that we're interested in? And there are various problems with smaller samples, right? So it increases the variability of the distributions, meaning that we have inflated type 2 error rates. And here's a great study just exemplifying this problem, right? So there's Schomburg and Perugini, where they sample a given population, and they run the statistical test every single time that they have a new participant. And they bootstrap it, which means they just sample the same distribution again and again and again. And what we see is that when we have low sample sizes, right, when the N is very low, the effect sizes are all over the place. They vary a lot, and they vary because we have such a small sample size. And what we actually see here as well, right, are that the trajectories can change from being very negative to very positive or moderately positive, and vice versa. So it's really important that we have enough samples, or a big enough sample size, to detect the power and effect sizes that we're interested in. So what we really want to be, right, is in this corridor of stability where we can reliably detect the effect size and the range of effect sizes that we're interested in. Okay. The problem of having a small sample size, right, is also that it's very difficult to interpret non-significant results, in the sense that we don't know whether it's because the results are null, right, whether there is no difference between the alternative and null hypothesis, or whether it's because the design is insensitive to the effect size that we're interested in. So that's why all of these things come into play, right? The size of the effect that we're interested in, we need to keep in mind, but also sample size and study design have effects as well. Okay, so now let's delve deeper into, well, what do we actually mean when we talk about statistical power? And here we have two distributions, right? A null hypothesis and an alternative hypothesis. And we have an alpha value of 5%, right? So that's the p-value of 0.05, indicating that we're willing to accept false positive rates 1 out of 20 studies, right? 5% of the time we actually have a null effect, but our statistical tests show that it's positive. Okay, power in some ways is related to the opposite of that. So we're willing to accept 20% of significant effects, of true effects, being falsely null, right? That's what power relates to. And power relates to the size of the effect, but also the sample size, indicating, which of course relates to the variability of these distributions. So if, for example, we had a sample size of 100, right, which we can see here, then we have a lot more statistical power. We have a greater chance of actually detecting effect if it's there. Okay, we only have a 3% error rate, indicating that, again, we can be fairly confident in the results if they do show a significant result. And again, if we look at the changes in the distribution, right, between the sample size with 50 and 100, right, we see a narrower range of effect sizes in the two distributions, indicating that, yes, a greater sample size really can give you a greater sensitivity when detecting an effect size of 0.35, for example. Okay, then let's have a look at what happens in the infancy world, right, in developmental science. This is sort of what we're dealing with, right? Here we have, again, the same effect size, right, 0.35. And if we design a study with 20 participants, we actually only have 47% chance of finding a significant result if it is there, right? So that means that around half of significant effects we can't even detect because our studies aren't sensitive to them. And here again, we see, right, the shaded part of the density distribution in gray indicates that, again, over half of the distribution shows null effects. So this is a really important concept to understand. And this is what we're going to be dealing with. So how can we really assess the dynamics between effect sizes and sample sizes and study designs as well? Okay, great. So let's talk about then how can we plan these sample sizes and what does it really mean to do so? And one strategy, right, to planning sample sizes is to look at studies that have come before you and then take exactly what they do and implement it in your own study. But I want to argue, and this is quite a bombastic statement, right? But I would argue that these sample size heuristics, as ways of determining samples or sample sizes are always wrong, in the sense that we can always do better. We need to justify why we have a given sample size for a given research question. In a similar sense to, for example, if we're designing a study with a specific set of stimuli, right, you also need to justify that these stimuli are actually related to the concept that you're trying to study. In a similar sense, we also need to justify that sample sizes are big enough to detect the effect sizes that we're interested in. Okay, that was, yes. And again, we know that there's this compromise between ideals and feasibility, right? So if we're interested in an effect size of 0.05, we can't collect likely 3,000 infants unless we have a multi-lab replication infrastructure, which we of course have here with ManyBabies. But usually when we're designing studies, we can't, it's not feasible for us to design this. So there is this compromise between ideals and feasibility, where we need to acknowledge resource constraints, right? But we also need to think very deeply about the inferential goals. What is it we're trying to show with this study? And again, I would argue that we need more nuance in that discussion, right? Or in those inferences that we can make. For example, thinking about what is the minimal statistically detectable effect, right? What can we actually detect with reliable with reliability, given the effect or given the sample size that we have. And we'll see this in a sec in the next slide. And again, right, to make dichotomous claims, which you do in null hypothesis testing frameworks, then we can reduce error rates, right, ad infinitum. We can keep on going. But at a certain point, right, we don't get any more benefit from increasing the sample size. So we also need to make sure that we're aware of the dynamics of increasing sample size and whether it actually contributes to power. And again, a compromise between ideals and feasibility can also be found in this optional stopping in Bayesian statistics. So I'd really recommend a paper by Many et al., which really looks into how much more efficient it is to use Bayesian optional stopping stats. And in general, Bayesian approaches are useful when you have very severe resource constraints. Okay, great. So there are two main approaches to justifying sample sizes, and one of which is to plan for accuracy. So this involves looking at the width of the credible interval or the confidence interval, and ensuring that you have enough participants to make inferences that you want to make given given the width of the confidence interval. So planning for accuracy is often again used in Bayesian statistics, and I saw some of the optional questions that you could ask. I saw that some were very interested in how to simulate data for Bayesian models, and we'll be doing that today. And you can use the approaches that we explore today to plan for accuracy as well. But what we'll mainly be doing is to plan for statistical power. So simulating data and then running models on them to see the probability of rejecting the null hypothesis. Okay. And if we really just take a pause and think about what the sort of threshold of 80% power really means, it's this, right? That the ratio of false positives to false negatives is 4:1, in the sense that we accept false positives. We accept false negatives to a greater extent than false positives. And this is important nuance to keep in mind, right? In the sense that we need to justify our thresholds by considering this cost-benefit analysis of sample sizes. We need to think, well, does an error rate of 30% actually make sense for this study, or does it not? Yes. Okay. Okay. Great. And this dynamic property of so construing statistical power as a dynamic property of design is again what I want you to get from this workshop. And thinking about which range of effects can we reliably detect? Can the study still design useful conclusions? And here's the figure I wanted to get to, which is where, for example, if we considered, or if we imagined we had resources for 19 participants. So on the x-axis here, we have participant numbers, and on the y-axis, we have hypothetical effect size. If we imagine that we have resources enough for 19 participants, this power curve analysis indicates that, so here's the threshold for 80% power. We actually only have enough participants to reliably detect effect sizes that are around 0.8, a magnitude of 0.8 in effect sizes, right? So if we're interested in anything lower than 0.8, then we're underpowered. Then we can't reliably detect the effect. So if we're interested in finding effects of around 0.35, right, we need more power. We need to increase the range of effect sizes that we can reliably detect given our sample size. Okay, so this is a nice dynamic way of thinking about, well, if we're interested in very strong effects, right, if we're interested in effect sizes around 1.2, 1.5, then we're actually fine. We can reliably detect these effects. So again, this is what I mean with relying on sample size heuristics from previous studies, where we need to be more nuanced in how we power for our studies using these sorts of power curve analyses. And a lot of you as well wrote in the question section, well, how do we power for effect sizes that we don't know, right? That haven't been meta-analyzed or analyzed in the multi-lab replication study. And I would argue, right, that we can never know the true effect size. And because if we did know the true effect size, right, there would be no reason to actually run the study. But what we do know, right, is the smallest effect size range of interest, right? We know that if we're interested in effect sizes between 0.5 and 1, then we know we need a specific amount of participants to be able to reliably detect these effects. So again, right, with that in mind, then we can never know the true effect size, and we always need to rely on this range of effect sizes of interest to power our studies. Okay, and again, this is really an opportunity to think through study design, right, and the cost benefits of a certain level of power. And I'll show an example on the next slide where we sort of investigate this question, right? Is it worth the increase in resources to reduce the error rate? Because if we reduce the error rate, right, there are limits to reducing the error rate in terms of the resources that they cost. So here I've made a sort of similar power analysis or power curve analysis with code that you'll receive in the tutorials. But here we see the interaction between the number of trials, so number of repeated measures, and sample size. And then we see statistical power on the y-axis. And here's the point I want to make, right, with that power is not just about sample size, it's also about study design. Because here, even if we have a sample size of around 50 participants, right, we're still at around the statistical power of around 0.8. And rather, if we have an infant experiment, right, where we can expose infants to six sets of experimental stimuli, right, we're already way above the power to reliably detect an effect size of around 0.3. Okay, so these curves, right, are important. It means that we can really design our studies and use power analysis as a tool to really figure out, well, which combination of subjects and items actually works. Okay. Great. And then you might ask, right, well, why should we then engage in data simulation? Why do you want to, why do we want to use this approach when we can use something like G-power, right? And simulation-based power analyses, I would start with a content warning, right? This is a rabbit hole territory in the sense that it's very easy to suddenly start exploring the multiverse of possibilities for setting parameters, for example, and really trying to, what should I say, be very conscious of the parameters that you're setting and their influence on the eventual estimates of power. And there are ways to counteract this. So we'll see with grid searches and so forth, but it is rabbit hole territory in the sense that there are interactions between parameters that actually matter for the power analysis. But again, that's the fun of it, and that's the flexibility involved that's useful in simulation-based power analyses. And again, a lot of the questions that you had when signing up for this was that you wanted to learn how to run power analyses for multi-level models. And user-friendly software, right, is often not appropriate for these sorts of complex study designs. And anything user-friendly, right, especially in the realm of something that's not very user-friendly like statistics, we should often be skeptical about. It's very easy to set an effect size and sample size and get a result, but often it simplifies the problem to, for example, a t-test and has no relationship to your actual study design that you're going to run. Okay, so simulation-based power analyses we can make tailor-made flexible statistical models. For example, I made this, right-skewed distribution of looking times. I made this by changing one line of code in the simulation functions that you guys will have available to you. Building up, right, this right-skewed distribution where we might have an experiment where we have looking times between 0 and 1 minute. And suddenly we have these right-skewed distributions, which we can then model and figure out how to model by using the simulated data in our models. And the reason why they're so flexible, right, these data simulated power analyses, is that we can use them for almost anything. We can use it for linear mixed effects models, generalized linear mixed effects models, structural equation models, Bayesian models, you name it, it usually starts with data simulation. And so data simulation is this powerful tool to really figure out, well, what's going on in the data and how can we model the data? So we used it these were some of the realms that we explored with the ManyBabies 5 power analysis, right? What happens if we have a certain number of infants dropping out after 4 trials, right? Missing data. What happens if we have heteroscedasticity, heterogeneity? How can we estimate the bias in terms of missing data and so forth? This flexibility you don't get in these user-friendly tools, right? And I would also argue that data simulation really forces you to make a decision about a given parameter. You need to make a decision because otherwise you can't simulate the data. So it gives you a better understanding of what's going on in the model. Okay, so let's talk a bit more about the process of data simulation, and then we'll send you out into breakout rooms, and then you can, get more practical experience with it. Okay, and what is a simulation-based power analysis, right? Now we've talked about the benefits of it, but what does it actually do and how does it work? And the basic sort of premise of a simulation-based power analysis is that we simulate data with a known effect size. We run hundreds of models, the models that we're interested in. So it could be a linear mixed effects model or generalized linear mixed effects model, so forth. And then we calculate the proportion of models that reject the null hypothesis, right? The proportion of models that find a significant effect, meaning, well, how many times out of the hundreds of models that we run do we actually find significance? And that will, of course, correspond to power. And what I'll ask you to do in the tutorial would be to look at a domain that we're fairly familiar with, right? So individual subject looking times across speech styles. So I've taken inspiration from ManyBabies 1, right, which is where infants were exposed to IDS, infant-directed and adult-directed ADS speech stimuli, and then their looking times towards a central, some sort of central visual stimulus was recorded. And it looks something like this, right, where we have a longer looking time response to IDS over ADS. Okay, I think I have it here, yes. And the statistical model of the data generating process, right, it might look like the following. So we might have something like looking time, right, is equal to a overall intercept for ADS, right? We know that infants will react when we play some sort of stimulus, speech stimulus to them. In this case, ADS, right? We have varying intercepts, so we can't imagine that every single infant will respond in exactly the same way to hearing ADS, right? We have some jitter around the intercept. We also have jitter according to the item, right? Every single stimulus item won't be the same. There'll be variability there. So we have a varying intercept term. We then have a varying slope term because we can't also assume that every single infant will react in exactly the same way to hearing IDS over ADS, right? So the varying intercept or varying slope terms of each subject, so these are the points here, they differ, right, according to which infant we're looking at. So we have varying slopes, and then we have some random error here, okay? And what we're doing in the data simulation process is simulating parameters for every single component of this data generating process. Okay, so simulating from a distribution of, for example, intercept terms for stimulus items, then we simulate from a normal distribution and say, well, we probably have some sort of variation between this and that, right? Similarly, we simulate for the varying intercept and slope terms. We do this from a multivariate Gaussian distribution. And again, that'll be explained in the tutorial, but I thought it'd be useful here as well. And basically what we do is we sum up all of these individual parameters of variability, and then we end up with a distribution like the following, which we can then model, right? Okay. Again, the flexibility of this approach can't be emphasized enough. So in the tutorial, you'll also be asked to code up an interaction effect between age and speech style. And again, some of the questions in the question sheet were, how do I calculate power for interaction effects? And this is fairly easy, right, in the simulation approach, because we can simply add an age predictor and then model it as an interaction effect. And here we see the IDS, right, shows, so as infants get older, they also respond more to IDS, we could say. They have a stronger effect, which is something that might be the case, right? Okay, so now it's your turn. So we'll arrange some breakout rooms, 5 to 6 people per group. So I guess that's what? Yeah, I'll calculate that in a sec. Wait. But then I've made a Corto website, so we can download the RMD files, our markdown files, and I'll provide the link in the chat. And again, I said that non-R people are also welcome, which they are. But please help them, R people, because I think it would be useful if they can learn from you. Okay, so here's what the website will look like for you. And for the ones who don't, so you'll download the exercise sheet here. So just download the first one. And here's what it will look like if you decide just to go through the R markdown file, then you'll get all of the visualizations here. Okay. So let me see. So that should be in the chat now. And should we have something like 20 breakout rooms? That makes sense. Okay, and then I'll come around to the breakout rooms. Great. Okay. Yes. Like Heidi, I also hope that was useful. And a common question that came up when I was visiting the breakout rooms, and Quinn said the same thing, is that, well, how did we actually discover or how did we set those parameters, those parameter values, right? Did we just rely on intuitions? Did I make it up? And the answer is yes, I sort of did make it up. And that's exactly what I wanted you to feel, that in this simulation process, right, we're forced to make certain decisions about certain parameters. And it can feel arbitrary doing so. And in this section, I actually want to argue for how we can do that in a better way, and maybe also how we can measure the influence of those decisions. And this shouldn't take long. This should take maybe five or 10 minutes, and then we'll go back out and then look at more informed decisions based on setting parameters. And now you've gained familiarity with simulation, right? Data simulation. And how do we set these relevant parameters? And again, this is just what I said, right? Reliance on these intuitions about infant looking times that we maybe have and that may be right or maybe wrong really creates this multiverse of parameter settings where we don't know what the influence of setting a certain parameter in a certain way is. And we need to be aware of those influences. And here, I would argue that cumulative science plays a really important role in the sense that if we see scientific advancement as this iterative procedure of data accumulation and synthesis through, for example, multi-lab replications like ManyBabies does, or meta-analyses, then we can use these resources to feed into our parameters to design future studies, right? So there's a feedback loop between what we know and what we are planning for, in a sense, in these data, in these para-analyses. And in the next exercise, the RMD files, then you'll look at converting the IDS preference effects to effect size distributions. And we'll see distributions like this, right? So where we have an effect size of around 0.35, for example, which was found in ManyBabies 1. And it also, and I had a long discussion with Julian as well about this, that maybe we actually need to focus or shift our focus to these cumulatively driven research projects where we can power or we can increase the power by really trying to synthesize across studies, figuring out where the variability and heterogeneity really are in these studies. So again, how can we set the relevant parameter settings? And here is, for example, a figure just from recently accepted study where we actually compare ManyBabies 1, the multi-lab replication, to a meta-analysis of the literature. And here we again find an estimate of around 0.35 across, which is consistent across the two sources of evidence. So again, if we're planning a study to do with the IDS preference, right, then we need to take the best estimate that we have available, which is from these cumulative resources. Another way we can actually check the effect of setting these parameters would be to conduct grid searches. And I think grid searches they take a lot of computational power, but they are worth it in the end, in the sense that, well, what's the effect of setting the trial number to 6, for example? We can also do the same effect, or we can do the same for different variables, right? We can say, well, what's the effect of setting intercept variability to 0.2, to 0.1, and so forth? And what's the interaction between all of these different parameters on power? Okay, what should we not use in power analyses? And I'll go quickly through this because it's better if you get practice with simulation and power analyses. I would beware of inflated effect sizes in past research. So I've just said that science is iterative, but cumulative science is where we need to really get our estimates from. And there's an approach called the telescope approach, where it's sort of a conservative estimate of power and study design, where you can design your study with that in mind based on previous research and taking this inflation into account. Pilot studies are biased, right? So small sample sizes in pilot studies, they often provide more variable and unreliable effect sizes. And then we also have a follow-up bias, right? So if we do a pilot study which has a large effect, we are also more inclined to actually test that study in future studies. And therefore, we're often underpowered on average if we rely on pilot studies. And then post hoc power is misleading and unnecessary and doesn't really make any sense. So some of you asked that question in the questionnaire again. If an editor asks you or a reviewer asks you to do a post hoc power analysis, also known as observed power, just don't do it. And there are many studies you can cite for this. Basically, it shows exactly the same as p-values. And there's a straightforward relationship between post hoc power and p-values. So again, if editors tell you to do this, don't do it. Okay, so again, now you know how to simulate data. Now we're going to try and be a bit more informed about the choices we make about different parameters. So relying on the ManyBabies 1 estimates of, for example, subject level variation and estimates of effect sizes and so forth. So really trying to be cumulatively driven in setting the parameters. Yes, so you can have a look at simulation-based power analysis. So that's just the second RMD file on the website. Yeah, then we'll meet again maybe in 10 minutes, and then we can take some quick questions.
Nope, Chris, you're muted. Oh.
Yes, there we go. I can unmute. That was yeah, great. Okay, so I mean, I don't have much more to say. So there were some error messages and some, yeah, again, fun errors, which we've never heard. If you keep getting errors for fill alpha, that's a problem with ggplot. So then you should update your ggplot. Then it won't come up. Yes. Yes, and Niloufar, I'm not sure I understand your question entirely, but if we have more than one effect size, right, then choose the one that's most appropriate to your research question. I'm not entirely sure, without having the actual context and study at hand. I'm not sure I can really answer that in full. But what I hope you've all got from this, right, is that I think there is some nuance to power analyses, right, to simulating data. And it does, to a certain extent, right, rely on intuitions and on your domain-specific knowledge about it. But there are ways to counteract bias and in a way, we should view power analyses as tools to, again, aid with study design rather than simply threshold measures of do we have enough, right? Making it dichotomous, which it isn't. And I think simulation-based approaches really, again, force you to yeah, know what you're doing, right, in a sense. And the code sessions, right, were you didn't have a long time for them, but the code will be available for you. So you can always check and try to figure out what means what, and you can ask me, and I'll gladly go through it with you. But any questions at the end? Before we head off? The boundary singular fit is also a example of the model fitting. So that's when the variance is variability is very, very low. Then it often gives this warning. So it's not an error, but it's a warning. Yeah. Did someone have their hand up?
Yeah, Nilufar did for a second. If you want to ask any follow-ups or clarify, Nilufar, feel free to unmute. If you can, there we go.
Okay, thank you. Can you hear me?
Yes.
Okay, I asked a question, and I mean that, for example, in my study, because I have more than one variable, and both of them are important for me, and because I want to choose the effect size based on the previous study that I have. But for example, different studies suggest me different effect sizes, and I don't know which one I should choose.
Right. Well, there I would say, right, again, if we don't consider it as a threshold, right, then you just need to ensure that you have enough statistical power to detect that range of effect sizes. So I'm assuming one is smaller than the other.
Yes.
Right. And that's fine, right? But you have to be able to, your study has to be sensitive enough to detect the smallest effect that you think will be there. That's how I would approach it anyway. Yeah.
For example, can I conclude that, for example, I can choose the smaller effect size because I want to be more conservative? Because,
Yes.
for example,
Yeah.
because one of them offer me, for example, 100 participant, and I think it doesn't make sense according to the resource that I have. But another one offer me, for example, 38 participant, and I think
Right.
if I want to be more conservative, it's better to choose the smaller one.
Right. I mean, conservative is probably the way to go, right? But again, with nuance in the sense that, well, are those the effect sizes you would expect?
Yeah.
Yeah. So that makes a lot more sense. Thanks for clarifying the question as well.
Thank you very much.
Yes, and there's a feedback form for you all to take. And yeah, please use the website and code and yeah, whatever you want.
Okay, so we're at time. We'll hang out for a couple more minutes if there are any more questions, but I just want to thank Chris for leading this workshop. And yes, I put the link to that feedback form in the chat. Please take a minute. It's very short and quick, but it will help us plan future workshops. If you take 1 minute to fill out that feedback form. So thank you, Chris, and thank you everyone for coming.
Thank you for coming.